Look closely at the smartphone right in your hand. Underneath that smooth glass is a chaotic, elemental war zone. Our devices rely on a forced alliance between two opposing periodic forces: unyielding, structured metals and volatile, unpredictable nonmetals. These early circuit boards and microchips represent the physical reality behind our digital lives. Every line of code is eventually translated into a pulse of electricity running through base elements pulled directly from the Earth. If engineers fail to balance this microscopic tension between indestructible structure and explosive chemistry, the technology self-destructs. Metals don't exist purely in nature. As seen in this open-pit mine, they are trapped inside rock and sand as minerals, scattered across vast landscapes. Separation begins with pulverization. This industrial machinery is used to physically crush massive boulders into a fine, microscopic powder. One way we isolate the metal is through the hydrolytic method. High-pressure water washes over a vibrating groove table. Because metals are incredibly dense, the heavy particles settle into the grooves while the lighter soil is swept away. We also use magnetic separation. Crushed ore travels down a conveyor belt over a magnetic wheel. The iron particles snap toward the wheel, while the non-magnetic rock waste drops into a separate bin. Sulfide ores require froth flotation. We mix powdered rock into a tank of water and oil, agitating it with compressed air. The oil-coated metal attaches to rising bubbles, forming a sparkling froth at the surface, while heavy waste sinks to the bottom. These blast furnaces perform the final purification. Through roasting and calcination, we use intense heat and oxygen to burn away the remaining chemical impurities. This sequence of mechanical and chemical stress is the necessary process for producing pure, industrial-grade metals. We prioritize metals for their malleability and ductility. This copper can be stretched into microscopic wires that carry electricity without snapping. These solid, unyielding characteristics provide the physical scaffolding for our infrastructure and megastructures. However, nature includes anomalies. This thermometer contains mercury, a metal that exists as a liquid at room temperature. Other metals subvert expectations of strength. Gallium melts from the heat of a human hand, and sodium is soft enough to be sliced like food. Material scientists utilize both the indestructible strength of traditional metals and these softer anomalies to build hardware for extreme environments. The rivals to these metals are the nonmetals. They are the wildcards of the periodic table, existing mostly as invisible gases or brittle solids. These elements are defined by their volatility. Phosphorus is so reactive with oxygen that it combusts the second it touches the air. It must be kept entirely submerged in water to remain stable. Their chemistry is unpredictable. While nonmetals generally ignore acids, they trigger violent, bubbling reactions when introduced to strong bases. They also lack the physical endurance of metals. Hit a solid nonmetal with a hammer and it shatters into dust. The major exception is carbon. When engineered into a microscopic weave, it creates carbon fiber, a material with the weight of a nonmetal but immense strength. Nonmetals act as renegades, providing the reactive energy and lightweight structures that traditional metals cannot provide. Modern tech exists where these two forces collide. It is the intersection of heavy molten heat and toxic ethereal gas. Metals construct the unbreakable electrical highways of our devices, while nonmetals provide the complex chemistry required for processing power and energy storage. A smartphone functions as a controlled chemical container. It relies on a continuous, microscopic war between structure and reactivity to stay operational. We have mastered the structural strength of metals, but we are only just beginning to harness the volatile potential of nonmetals. As we push the limits of physics, we have to ask, which side of the periodic table is truly driving our future?